be going over the second concept for Axel contest number 3, which is data structures. So first thing we're going to be looking at are stacks and queues. This is the easiest part of this section. Okay, so the commands that we're going to use for stacks and queues, they're both the same, but they have a little bit of different functions for each stack and a queue. So both have the same push function, which puts, let's just say we're doing push A, it pushes the key A at the top of the stack. So you can imagine a stack to be like a stack of pancakes or whatever, and the push would add this pancake A to the top of the stack. Now for stacks, the pop function removes the top item of the stack. So if we were to pop a stack with an A at the top, if we do pop, it'll return the A value. And for queues, that's different. For queues, it'll pop out the bottom value. So if we had a queue with a bottom value of A, and we do pop, it'll return the value A. And if the queue is empty, in either case, queue or stack, and you pop something out, it'll return a value called nil. So let's do a little practice. What does the following program output for a stack? So for a stack, we would, so for a stack, we have, first one is a push Y, so we have a Y, and then we have an E, which would, for a stack and queue, put it to the top, so then we'd have this, and then finally S. So this is what the stack would look like. Oh, I'm sorry, there's a Y there instead of a S. So this would be what the stack looks like. And now X equals pop, and you remember pop takes the topmost value, so X equals S, and then Y. Now S is gone. Now this is the rest of the stack. And now Y equals pop, so we take the top value, which is E, so then Y equals E. And then we want to print X and then print Y. So that would result in S and then E as the output for that problem for a stack. And now let's do it as a queue. So queue, very similar process. Oh, that's a terrible one. Okay. Alright, similar process. It would look the exact same because the push is the same for both. But now X equals pop, and for this, for queues, we take it from the bottom. So X would be the bottommost value, which is Y, and then Y would be the new bottommost value, which is E. And then if we want to print X, Y, we would just print Y, E. Like that. Okay, so now let's do a real Axel problem. Consider an initially empty stack, so it's a stack. After the following operations are performed, what is the value of Z? Okay, so we know this is a stack, so let's first create it. Push 3. And then it would be 6, so 6 goes on top of 3, and then 8, so 8 would be on top of all of them. So this is our stack, 8 on the top, and then 6, and then 3. So now Y equals pop, and since it's a stack, we would take the topmost value, so Y equals 8, and X equals pop, so now that the 8 is gone, X would equal the topmost value, which is 6, and we push whatever X minus Y is. So first X minus Y would equal 6 minus 8 equals -2. That is not a 2. -2. Okay, so now we want to push -2. So right now our stack looks like 6, 3, and then since we're pushing the -2 would go on the top. And then now we have z, which is just pop, and since it's a stack, z equals the topmost value, which is -2. So that would be the answer for this one. Z equals -2. Okay, now we're going to be going over binary search trees, which is where stuff starts to get a little bit complex. So the structure of binary search trees is very well explained in this video. I will not play it now, but it's linked in the drive. You can watch it whenever you want. I'll be explaining it here, and hopefully you got it in class too. So let's first do a simple example of the word yes. So the way binary search trees work is it deconstructs this word into its letters and then makes it easy to find each of the letters. It's super simple for a 3-letter word, but as you get more complex, it gets more useful. So we always start for binary search trees with the first letter, which is a Y. So regardless of what the letter is, we always put it at the top of the tree. So that's step 1. And the values for these letters are associated with their place in the alphabet. So the earlier they are in the alphabet, the lower their values, and the later on they are in the alphabet, the higher their values. So now we're done with Y. Then we look at the next letter, E. E is less than Y, because Y is at the end of the alphabet, E is at the beginning. And if it's less than its preceding letter, so E is less than Y, then we put it to the left of Y. A row down, but to the left of Y. So it would look like this. And now that we have Y and E, we can move on to S. So now S is also less than Y, because Y's at the end, S is like near the middle end. So S is going to be to the left of Y, but E is already here. So we need to compare S to E. And S is greater than E because S comes after E in the alphabet. So S is going to be to the right of E, but to the left of Y. So it's on the left-hand side of Y, but the right-hand side of E. So that is how you would do that for the word yes. Super simple. And now let's go over the attributes of binary search trees. So you're going to have to know these words, and they might ask you for them on the test. So the root is the first letter of the tree, which is Y. We went over that. The depth is the depth of the deepest node, and that would be, for this one, 2, because S is 1, 2, like depths away from the top. An external node is not usually drawn on the trees because it's kind of distracting. So I highlighted them here in red, and in the last slide you can see I didn't write them because you're not going to see them. But you need to know they exist, and they might ask you how many there are. So here, there are any additional nodes that could be added to the existing nodes that happen. So I could add one here to the Y, there wasn't one here, and each node can only branch off 2. So that's why there's only one here. And then the E was also, could have done one more, so there's another one there. So there's 2 external nodes. The internal path length is the sum of the depth of all the nodes. So the depth of Y is 0, the depth of E is 1, and the depth of S is 2. So 0 plus 1 plus 2 is 3. So that's the internal path length. Then the external path length is the sum of all the depths of the internal and external. So we have 0, and then E is 1, and then this one would be 1 as well. So now we have 2 so far, and then S was 2 we got, so it's 4 right now, and then this depth is also 2. So it'd be 4 plus 2, which is 6. So that'd be the external path length. Alright, practice question. Build a binary search tree for the word American. And this is an alphabet that's just referenced, so you can easily see what values are greater and less than, and all that. So here we can see it is, so we can do it now. Let's start first with the A, we always do, and then next we have an M, and M comes after the alphabet of A, after the alphabet for A, so we'd write M here, and E is also after A, but it's before M. As you can see, E is here, M is here. So we're done with A, we're done with M, now we're at E. E is less than M, but still greater than A, so we'd write E here. We're done with E. Now R. R is after A, and it's after M. So the R would go to the right of A and M. And now we're at I. I is right here. It's between E and M. So it'd be, so it's after A. It's before M. And then for E, it is after E. So I would be right here. Now C. C is after A. It is before M. And it is before E. So we would write the C here. A. For Axel, we are going to treat duplicates like they are less than or equal to their corresponding one. So the A here would be less than or equal to the A here, and since it's less than, it would be to the left of A. So now we're done with that. And last one, N. So N is right after M. So it is after A, it's after M, but it is before R, so the N would be to the left of R. So that is what the tree, binary search tree, would look like for the word American. And we can see here that is indeed what it looks like. So now let's move on to priority queues, arguably the most difficult topic in this section. So the basic premises of these ones are that they're two properties. So each node is less than or equal to its children, which is just the ones directly under it. And there has to be no holes, and we need to go top to bottom, left to right. So those are pretty simple, but it can get pretty complex. So let's make a priority queue for the word hello. Okay, so here we have hello. Let's start with the first letter, which is an H. Now we have an E. We always go top to bottom, left to right. But we see here that E is less than H, but we want the children to be greater than their parents. So we have to switch these out. So this would become an H, and this would become an E. So we're done with these two. Now we have an L. So top to bottom, left to right is there. There's no conflicts there. Next L, top to bottom, left to right over here. And L is after H, so there's no conflicts there. And so now we have O. This is the next available spot. O is after H, so there's no conflicts there. So the final tree without all the scribbling would be E, H, L, L, O. So, and we can see that that is indeed what it looks like. Alright, so hopefully that explained everything pretty well. And yeah, that's about it for the math short answer questions for contest 3.